Dames en heren.
Ladies and gentlemen, I hope you enjoyed the coffee break and that I can encourage you to tone it down a little so that we can move on to our second lecture. I'm pleased to introduce Mr. Lieve de Witte to you. He's our next speaker. Mr. Lieve de Witte is from the advisory engineering firm Nieman, which is dedicated to construction physics, technology, and regulations, and his presentation is entitled Objective-Based Fire Prevention. And what's particularly interesting, I'm pleased to tell this to Mr. de Witte, if we recollect Mr. Merci's lecture, he basically says that when you don't have a fire, it's awfully difficult to validate certain systems and to know what they do. It's also difficult to formulate fire safety requirements. So we're fascinated to hear what Lieve de Witte will tell us about this subject.
Ja, dankjewel voor deze introductie.
Thank you for your introduction. Now, very briefly, let's see how this works.
Welk? Hij doet het niet. Misschien kan iemand me even...
Help me here, please.
Dat schiet lekker op.
We're batting 1000 here.
Laat het nog één keer zien dan.
Oké, nou, ik begin dan maar vast even nog met een korte introductie van mezelf.
Well, briefly about myself. I'm Lieve de Witte from Nieman Consulting Engineers. I'm the fire safety consultant. And at the IFV here, I'm a visiting lecturer in fire safety training, including fire safety engineering. Thank you. Perfect. And I was seconded for the State Building Service as a fire safety engineer. So I'm involved mainly at the front end of operations. And I'm from the practice, but I see very few fires in practice. And I'm peripherally involved in the trials in Zutphen, but that's also very peripheral. This shows me in a different capacity. In safety engineering, they often describe safety as a deliberate experience of risks. I'm taking a certain risk here, and the question is whether this was deliberate. Retrospectively, perhaps it may not be, because one of those shopping carts can handle about 110 pounds. Well, I'm slim, but I'm not that slim. So you might say that the subconscious experience of risks figures in our fire safety in buildings as well, because we observe rules and think that they feel safe to us and comfortable. So we accept a residual risk without knowing what that residual risk is. So how aware are we of our risks? If you look at rule-based, you might encounter these situations. I don't know whether these all relate to rules, but I'll tell you about a few of them. At the upper left, they decided they wanted a sign warning us about geese. And there is a warning sign there. But we don't have a picture of geese, so we put a cow on instead. So you might wonder, what do you need to watch out for, cows and geese, or neither of the above? At the lower right, there's a road here. And apparently there are a lot of things you're not allowed to do, so perhaps you'd have to stop and take a look to see what's not allowed here. And probably you need a sign to denote every single rule and prohibition. And what went wrong at the upper right, you don't know whether that relates to rules. Perhaps each apartment at the upper right needs to have a balcony, whether or not the balcony is accessible. Well, that's pretty odd if you wind up in one of those buildings. Now, if you look at fire safety and look at the middle two pictures, well, they're entirely in compliance with the rules. You see that TU Delft, which is burned down, and you can see that a burned out building fits perfectly within our regulations. And we thus accept a lot of risks. Now, zooming in on those regulations, if you look at the Construction Act, there are two targets: preventing casualties by fire and preventing fire damage to adjacent premises.
Uitgebrand.
Think of those pictures. It's perfectly easy to have a building burned down without any victims or the fire spreading to the adjacent buildings. And the other targets don't figure in our regulations. Think of loss prevention, whether it's material or immaterial, or social damage, or sustainability. Those are private objectives, and they're not regulated. Well, what do the regulations serve? They concern rule-based performance requirements, which target safeguarding a certain level of fire safety. There are no specific objectives in the order of magnitude of victims or loss, and the safety consequences of those buildings vary. So you can have one set of regulations, but they don't have the same safety consequences. And the principle is ideal use of buildings. And you need ideal building users. Well, you can beg to differ on that, because building users are not ideal and they do what they think best. Now, what matters most? Rules or objectives? About the rules. If you look at them, what happens with those performance requirements? You review the threshold value for each order of magnitude, which means that the review is not qualified at all. Either it's satisfactory or it isn't. Often there's no cohesion between the different orders of magnitude and units. So that's why rule-based review needs to be straightforward and easy to emulate, but the result is that you haven't optimized fire safety. So if you look at escapes and evacuations, there's a distance and a width and a flow pattern and mutual cohesion, and that mutual cohesion defines the fire safety level. And fire is often approached as a single unit, one of a kind. For example, buildings have a certain thermal load, so fire conditions such as the source of the fire and how the fire manifests, as well as the building and the consequences of that building for the scenario, as well as the user features, are rarely taken into consideration. Well, you could say that you need to do this when you want rule-based fire safety and fire prevention. For example, with aging demographics and with the same rules, you're likely to have more victims because the elderly become less and less independent, and evacuation takes more time. So objectives are more important than rules. And you can say that objective-based fire prevention sounds nice. How do I implement this? First, you carry the two objectives from the building regulations over into sub-objectives, and you could identify those by considering the functional requirements from the building code. They could be safe surroundings, safe building. Think about the structures, safety compartments, and safety of escape routes and safety of attack routes. Well, this sub-objective might be nice, but how can you quantify it? You could consider the acceptable failure risk, and that won't really help you because an acceptable failure risk is not defined anywhere. You might assume that a lower acceptable failure risk will be inversely proportionate to the safety. How do you determine the acceptable failure risk? You can compare it with a building that directly meets the regulations, or you use it as a benchmark to determine the acceptable failure risk. And those sub-objectives are linked. You can imagine that failure of a compartment will affect the safety of the surroundings and the safety of escape routes. You can assess those sub-objectives separately. So in your working situation, you need to perform the same assessment of the failure risks if the building would not meet the regulations. If you allow a higher failure risk, you'll need to offset that and compensate it by reducing the acceptable failure risk in another sub-objective. For example, at the upper right, you see an industrial function with 2 compartments, 2,500 square meters. For the safety of a compartment, you directly comply with the building code, but for the safety of the surroundings, you'll need to realize a certain distance to meet the threshold values. You can achieve this by calculating the radiation of the facade. Well, if you enlarge this by 2, obviously the safety of the surroundings requires a higher safety level. You'll need to enhance that projection to get the same safety level. But what people often overlook is that the failure risk of that compartment has doubled. So aside from needing to increase the distance, you need to redefine the threshold values for the surroundings and make them more rigid. So if the failure risk in one of the subsystems doubles, the others will need to be halved to have the same risk level. This is often overlooked in equivalent solutions. Usually they focus only on the effect. They don't consider the total failure risk or the total risk of those subsystems combined. Besides, you need to consider the boundary conditions. I mentioned it earlier. If you look at objective-based fire prevention, you need to consider the fire, and you can make something project-specific only if you look at the specific building in a fire scenario. Now, fire conditions such as building, interior arrangement, and opening factor all figure. And their role may vary depending on the sub-objective. Take the building boundary condition. If you're looking at the safety of the surroundings, you don't want the fire to flash over outside the building. And if it does exit the building, it's more likely to be dangerous to adjacent buildings. That's a high risk. If the fire is small and contained in the building, then the risk to the surroundings is very limited, and you might say that's less dangerous. Well, if you have a large building in between or a large facade, that is more of a burden to adjacent premises. But the opposite holds true for escape routes. With escape routes, you might want the fire to be outside the building, and then the smoke and heat are exited, and the escape routes remain intact for a long time. But it's more dangerous if it's a low building, because then the escape routes are obstructed very quickly. With a higher building, there's some buffer capacity so that the escape routes can be used longer. Now, objective-based fire safety. You could subdivide the way of doing this. I just suggested you could work with sub-objectives and failure risks. Specifically, I've listed 3 methods. You could assume the natural fire concept. I mentioned this earlier. It's important to look at the actual fire capacity scenario. So trying to predict at the front end what fire scenario would materialize in a building. You can also calculate the thermal load on persons and structures more realistically, and based on that, you can assess for that building whether the risk is acceptable. At the lower left, you see in the graph there are 2 lines plotted. The first is the input. So you input a certain fire scenario, and the second is the output. So what happens? And with fires, there are various stages, and you have a local fire, which is often not the decisive incident. It imposes a local load and may obstruct escape routes near that fire, but at a certain point the temperature in the space rises so high that there's flashover, and that changes from a local fire to a compartment fire. And the compartment fire is often the decisive incident, as we notice in our regulations, which emphasize the link to a compartment fire with a certain thermal load according to the standard fire code. And if you look at the building carefully, you can determine that burden per project. So then you have a specific thermal elaboration of fire prevention. Another option is to adopt a risk approach. For example, one based on the cascade model. And the steps in the cascade model are a matter of opinion. You could include the same stages as in the graph as links. And this risk approach is not necessarily project-specific. It becomes project-specific when you take a look at the project-specific provisions. However, if you don't use an actual fire scenario, it remains a generic method. We still think in terms of a compartment fire related to a standard fire code. A combination of both would assume both risk factors that determine the likelihood of failure in that step and the actual fire scenario at the front end. That way you can assess your failure risk into a fire scenario, and then you get a customized solution for that specific building. At the bottom right, you see the list of features. That's from the book Foundation for Fire Safety. You have fire features, building features, and people features, and you'll need to assess those combined. Our regulations include them minimally or not at all. Now, here's an example highlighting the natural fire concept. You see the hospital in Amsterdam, the OLVG. It has a central disclosure route via the light street, and that's denoted here as 1A and 1B. You enter here. This is the central access pathway. These are large movement areas, as indicated on this photograph, large long walkways, and there's some police squares for specific clinics where people wait to visit the ambulatory clinics in the adjacent spaces. So these areas. And these ambulatory clinic spaces have an input and output system, which has a natural mechanic input and output, and was once dimensioned to enable a local fire scenario and to safeguard fire safety based on the idea of a small fire in one of those larger walking areas. Now, the partitions between the ambulatory clinic area and the adjacent compartments require a VBDO of 30 minutes. Now, this WBDO cannot be foreseen in the structure. The structure does not allow fire resistance for 30 minutes. Well, the glass is, but the window frames are aluminum, and you all know that aluminum will succumb. So the risk is that those frames will succumb to the fire. If you were to follow the rules in fire prevention, you would simply replace everything. So you would replace the frames to include, to accommodate 30 minutes of fire resistance. The question is whether that is necessary. And you might say that the buffer space adjacent to those partitions might be provided for by the WBDO. So you restructure the WBDO. I'll disclose this based on these three figures. The top two reveal the building code, so how the building code accommodates the WBDO requirements. As for the interior, the WBDO automatically yields fire resistance. So the partitions ensure 30 minutes of fire resistance, and they don't allow for the buffer effect of the space in between. If you look at the exterior structures and the distance between both structures is sufficiently present, then an infinite buffer effect is assumed because smoke and heat can exit here, and you don't really need a fire-resistant partition. So that means that you get fire resistance of 0. Now, the situation in this hospital is somewhere in between. The buffer capacity is considerable, but it's not infinite. So rule-based 0 to 30, you can't pinpoint it in between. You can pinpoint it there. The WBDO is guaranteed through the existing partitions and the buffer effect of that space, which takes the facilities present into account, including the RWA system. Now back to the sub-objectives. We're dealing with the sub-objective of compartmentalization and safe escape conditions. So the idea is to gear fire prevention based on the likelihood of the failure risk. So the interpretation meets regulations. We do this by considering the buffer capacity together with fire resistance ability so that you get that required 30-minute window. At the bottom, a zone model is depicted. If you look at a realistic thermal load, they often use these zone models. As the previous speaker mentioned, perhaps we could run the video. What you see here is a simulated fire, and that fire and the fire capacity scenario is based on all the features in this building. So this considers the arrangement of glass and frames on this front. So the calculation has assessed possible courses for different settings, and heat and smoke might disseminate to the adjacent ambulatory space and the walkway, and then they see whether this space conditions in both places might not exceed the threshold value for flashover, because if they do exceed that value, then the fire spreads to other compartments. So what the RWA does is it keeps the boundary conditions low enough to avert flashover and spread of the fire to those other compartments. The temperature is depicted in far too small a range. That's why we have a graph disclosing the thermal load here. You can see the temperature on the y-axis, and you see the horizontal axis as time. So you see that after flashover, so after the glass on those facades has succumbed, then it spreads to the atrium, and with this RWA capacity, the temperature drops below the threshold value for flashover. So that way you're meeting the requirements. You can do the same to guarantee safety of escape routes. You could see the radiation load over time. Here's another example, a risk approach. You could apply a risk approach linked to the cascade model. Here you see a simplified structure of the cascade model depicting a few steps of 3 stages, and it always starts when the fire erupts. In this case, expansion to a local object, expansion to a local fire in space, and ultimately a total fire in this compartment. In this example, we examined smoke dissemination from a home to a stairwell, where the stairwell is directly adjacent to that home, as you often have in entranceways. They didn't focus on the fire expansion, but on the smoke obstruction that comes with that fire expansion. And the smoke comes before the fire in all cases. So when there's only a local fire, it's the area is already filled with smoke. So what you do at this point, if you run through the cascade model, you'll need to determine the failure risk for each step, and those failure risks are not established anywhere, so you have to either estimate them or assess them based on statistical data. Well, they made an effort to estimate it here, and you can see the equation. It's not so much the actual likelihood identified, it's more about the equation. And the equation is a benchmark situation that, once again, directly meets building regulations. So a home that is adjacent to a stairwell in a gateway, and since 2014, in the gateways of new construction, you need a certain doorstop. So they've assumed a traditional doorstop here. We compared this with a smoke alarm-driven doorstop. So the reliability is with a smoke-driven doorstop is slightly higher than with an ordinary doorstop. They compare this with a home that has sprinklers, fire sprinklers, and one that has the smoke alarms doorstop and the fire sprinklers. You don't need exact figures because this is an equation, a comparison, both in the benchmark and in the actual situation. Those figures are identical, so it doesn't really matter how high or how low they are. The extreme appears here, with the smoke dissemination from phase 1 to 2. In 90% of the cases, that smoke does spread, and that enables you to compare the different likelihoods in each stage. So you see the resultant factors, so the likelihood per situation, and in the final phase between a smoke alarm-driven doorstop and a normal doorstop, there's a considerable margin of difference. That's a matter of opinion, of course, but the reliability of such a doorstop is probably better than a standard doorstop, so that you are introducing a measure of safety. Now, to avoid dwelling on this specific example, this just shows one example of how you could structure your risk approach to target a solution. And this is basically a generic solution, although I said it's semi-project specific because you do consider the actual facilities present. Now, the final example, that's somewhat more abstract. When you start relating those risk factors to a realistic fire capacity scenario, you get a customized solution. To do this, you apply the risk factor to the physical fire scenario. So initially, the fire capacity scenario is based on the different factors of capacity within the building, and then you multiply that and apply the risk factor. If you're applying a sprinkler installation, for example, the likelihood of flashover in the space will diminish drastically and may almost be neutralized. So that leaves you to apply a risk factor that reduces your fire capacity scenario. It doesn't matter how high it is. What matters is the idea. So you see a risk factor of 0.57 that corresponds with certain specific active fire safety facilities that you have to add, and a situation where you do nothing and perhaps merely enlarge the compartment. So the possible result is that you have different scenarios with different capacities, which yield a different thermal load on structures or persons. In addition to the height of that thermal load, its duration comes into play. So we see that we have more, when we have more active fire provisions, then the duration drops. I won't elaborate on this, but if you simply examine the building code functions and examine realistic fire scenarios and compare them, then you'll see a world of difference. If a building is used as an office, then the fire scenario is entirely different from premises used as a shop or for industrial purposes. That means that reliability matters, especially in those project-specific custom solutions. What you can rely on is paramount. And we see a full sense of safety and reliability when we're talking about rule-based fire prevention, because they think that standard solutions are too reliable. But if you look at a shop that's got an interior arrangement, then the WDO may not be high enough. It may be much too low for thermal load. Whereas with a different function, such as an office function, that WBDO of 60 may be too high. So there's a false sense of safety with respect to rule-based solutions. So the objective-based solutions are jeopardized because people rely on rules. The moment we deviate them, we want to create a certain sense of reliability. And this reliability is simply achieved by believing somebody's pretty blue eyes. So that reliability is personal, and that's not right. The reliability should be determined by other factors. Now, in objective-based fire prevention, the way to achieve this is by linking it properly to the rule-based objectives. So you use the benchmark situation to disclose the residual risks that are accepted within the regulations, and then you see how reliable the objective-based fire prevention can be. Of course, the natural fire concept is based on a lot of principles. You need the principles to be robust, and that may vary depending on the situation, and there's no straightforward answer to that. What should be necessary is that you always need to perform a sensitivity analysis of the decisive fire conditions. In addition, you might want a sensitivity analysis that uses standard deviation. Now, this afternoon we'll have a workshop on reliability of fire safety objectives, which will elaborate on how to structure that reliability. That takes me to the conclusion. To sum up, objectives are more important than rules. Think in terms of objectives and try to get the solutions based on those objectives. It won't impede innovation, and with rules, innovations tend to be complicated. If you think in terms of objectives, you can solve any situation as long as you pursue the same objectives. Now, objective-based fire safety is possible by applying the sub-targets to structure objective-based fire safety. One is the natural fire concept, which assumes project-specific facilities, a risk approach, or a combination of the two. And if you go to customized solutions, you'll optimize fire safety, and the rules that we have might already be optimal, but that will give you a full sense of what's optimal. Now, the reliability of those fire safety objectives is very important, and that needs to improve. All too often, we simply ad-lib and don't have a clear sense of the reliability. Now, please run the video. What I'm trying to explain here is that you see one character going against the tide. That's the objective-based fire prevention. We don't do enough of that yet. The mainstream is rule-based. Let's reverse that and focus more on objective-based fire safety so that soon this pattern will be the opposite. Okay, that's what I had to tell you. Thank you very much for listening. Thank you very much, Lieve. That's wonderful to hear. And that was impressive discourse for using objective-based approaches. Are there any questions? Speaker is inaudible. Interpreter apologizes.
Hoe vaak is bij jullie bureau voorgekomen dat iemand van de winkel zijn brandveiligheid hoger maakte als dat de wetgeving voorschrijft in plaats van lager maken dan specificatoren. Daar ben ik erg benieuwd naar.
Ja, dat komt heel weinig.
That's very unusual. Hardly ever question about fire regulations for different types of premises. One factor here is I spoke about objective-based fire safety, where objectives are approached from that perspective. But with shops, private objectives come into play, so the added value to the shop owner should be embedded there. So he needs to want to pursue loss prevention for business continuity, or based on his vision about how he wants to approach it. Otherwise, it simply won't happen. Inaudible question. We keep trying to consider more private objectives in the guidance we provide, but first we notice that people request advice based on rules. So when we try to take that to the next level and to demonstrate the added value for the shopkeeper, it's difficult to make that clear, and they often choose the one-size-fits-all variety. So we need fire departments and insurance companies to help us there. Another inaudible question. Interpreter apologizes.
Veel meer doen dan de regels eisen. Als we kijken naar
Ik heb andere ervaring, maar goed, het
Nee, oké. Als we kijken naar grote winkeliers. Er echt heel bewust over na wordt gedacht. Albert Heijn, die heeft heel bewust naar hoe gaan we om met bedrijfscontinuïteit. Daar gaan ze naar. En dan gaan we hoeveel het in. En dan wordt er degelijk over nagedacht, op hoog niveau, hoeveel het in en hoe gaan we om. En uiteraard heb je daar een evenwicht te vinden in een balans in de economische aspecten die erbij vinden. Dus het is niet zo, ze doen het niet. Ik denk wel, we moeten kijken naar wat voor bedrijf kijken naar. Natuurlijk kijken naar een klein bedrijf, kijk er anders tegenaan dan een groot bedrijf. En zelfs een Aldi, bijvoorbeeld noemend, die kijkt er ook wel degelijk naar. Die bedrijfscontinuïteit is heel erg goed.
Het lijkt genuanceerd.
Well, it sounds like you've qualified that. I can understand both arguments because I can certainly identify categories that has difficulty limiting itself to what the regulations stipulate. But there are others, companies that have a broader safety policy. That's basically what you're arguing. And those are the best examples because then you establish that link with the insurance company because the insurance company may set other requirements. But I can sense that question. We cannot take for granted that organizations, companies, and institutions do more than what's required by law. Other questions? Here up front. No other questions. Inaudible remarks. Interpreter apologizes.
Als je geen private doelen nastreeft, dus in het minimum niveau wil zitten, en je wilt die winkel 2 keer zo groot maken, 2 keer zo groot als toegestaan, dat heeft liever net hetzelfde laten zien. Dan krijg je toch met andere eisen te maken voor boomoverslag. Dan krijg je andere eisen te maken voor je instandhouding van je infrastructuur. Dus het is niet zo dat hij daar dan helemaal niets doet. Het is dat hij maatregelen verschuift, zodanig dat hij zijn winkel bruikbaar kan maken. En dat vind ik een hele andere insteek dan altijd maar denken dat hij het onderste uit de kant wil hebben. Hij wil het optimaal ontwerpen. Dat is waar het om gaat. Zelfs als hij geen duurzaamheidsdoelen heeft.
Oké, dank.
Thank you. Here in front. You have the floor. Inaudible interpreter apologizes.
En als
Ja.
er natuurlijk nu allerlei alternatieven in fietst, zeg maar, en ook alternatieve vormen van gelijkwaardigheid. Wat nu ook gebeurt, hè, ziekenhuizen met mistinstallaties en zo. Ik moet je eerlijk zeggen, dat gaat harder dan ik het bij kan benen.
Ja.
En daar maak ik me wel zorgen in, zeg maar. Ik ben heel erg voor je pleidooi, dus dat ga ik niet verkeerd. Maar die
Question is about alternative solutions and different types of the repressive service. Yes, a very justified remark. My objective was to present you with a vision for objective-based fire prevention. I could have called it objective-based fire prevention and suppression, because what's happening here, approached from a realistic fire scenario, can serve fire suppression very well. Tomorrow, we'll take a look at those tests in Zutphen, which link simulations to actual fire scenarios. And in terms of assessing the effort that needs to think about the quadrant model at the front end, you can really use simulations to show the fire suppression services what to expect. So you need to connect those two, and it would be great if that happened far more. I couldn't agree with you more. At the back of the room. Inaudible interpreter apologizes.
Waarin je aangeeft dat voor het beoordelen van een gelijkwaardigheid je eigenlijk niet alleen het effect moet meenemen, maar ook de kans op het optreden erop. Dat gaat eigenlijk misschien weer een beetje aan de andere kant op. Wat dat betreft kan het voor ons dus nog een grotere klus worden om die gelijkwaardigheid goed te beoordelen. Sterker nog, je kunt niet alleen dan van een effect uitgaan. Aan de andere kant kun je dus ook veel mogelijk voor de aanvragen van gelijkwaardigheid om andere methoden daar tegenover te stellen.
Ja.
Want ik vind wel dat in deze discussie de aanvraag van de gelijkwaardigheid uiteraard bij de aanvraag ligt.
Uiteraard, ja.
Of course, yes.
Ja, wat ik in het kader van de eerdere...
Yes, relating this to the previous question, we see that we would really like to do that, and we can't always get that across properly. We don't have a chance to communicate that. To assess fire resistance likelihood is a very difficult task. Clearly, no two buildings are alike, and in many cases, the solutions assume likelihood of one, meaning that there will always be a fire, but the building regulation focuses on a certain conclusive effect, compartment fire, but there are some stages in between where you can apply facilities that will curtail the likelihood of flashover. Think of sprinklers. So the failure risk that I mentioned primarily addresses averting flashover and the ensuing consequences. I still have one question left, but I see one more from the audience. Inaudible interpreter apologizes.
Dat bij gemeente X wordt het wel toegelaten en gemeente Y weer niet. Is het misschien een idee om een soort database op te stellen, landelijk? Ik weet dat elk project allemaal verschillend is, maar dat je wel iedereen niet hetzelfde wiel hoeft uit te gaan vinden en wel of niet mee akkoord kan. Hoe je zeg maar hoe je zou kunnen verbeteren.
Well, how to improve for certain solutions to be applied. There are various opportunities. I'm not sure whether a database is the best way to achieve this because the project's specific nature of projects does not call for a database. The database would be based on input that you can apply everywhere. So then we're talking about generic solutions. The assertion is that you achieve optimal fire safety by reviewing the object as a specific project, and then you still have to see what types of checks and balances you need to include, and lots of people come into play there. How do you increase reliability? You might look for more second opinions in that certain companies or institutes could check and assess each other more. But that relates to ideal regulations, and I have some views, but I'm not going to elaborate on them now. My question is, in one of your slides you demonstrated that there are three large components: humans, fire, and buildings. As for the fire and the building, could you link prevention to suppression? Because it's certainly there when you need it, but I'd like to highlight the other components because the usual source of failure is human behavior, and we can think of anything possible. That would be one thing, and we can hope that the fire follows the course that we hope, aside from which way the wind is blowing and whether there's a door open. But as for the human factor, what about that? Once again, if you look at what's happening right now in the design process, the parties tend to be involved only if they are party to the design. So parties that see structural and technical facilities, the organization is often considered subordinate or receives no consideration at all. And when you look at objective-based fire prevention, you'll need to take a look at the organization. Think about nursing homes. There you need walkways where there's nothing happening and there can't be a fire, so that would be a safe area, and you could use those walkways for the evacuation for a longer period of time. In most buildings, the way they're presently arranged. There's insufficient consideration for that. So how do you accommodate those user features? You might need specific organizations that correspond with those users. It's difficult to attribute a set value, but you could disclose the thermal load on persons to buy time or assess a duration for a certain effect to manifest. But humans remain a factor of uncertainty. We need to wrap up. Even though a lot of other questions come to mind, this afternoon there will be a workshop focusing on reliability. I think that's already